Hi guys, Sajjad Hussain again with a new video. Actually, this video is recorded because of some requests coming from various sites. The request was coming from the students of in civil engineering, and they asked me to give a presentation on the very basic, or I can say elementary, structure analysis. So in this lecture, what I am going to cover is as follows. Like, first we will see statically determinate structures. What are statically determinate structure? What are the concepts? And how can we calculate the support reactions? And what are the sign convention for internal forces? And then we will go for method of analysis, like method of joints and method of sections. This will be only for statically determinate pin jointed structures. Now, to start with the concept, let's explain like this. Suppose I have 4 bars. Let me see like this. 1, 2, 3, and 4. All these bars, they have eyes on both the ends. So what is the purpose? The purpose is that I can join them through pin. So they will form a pin jointed frame, and they will form a pin jointed frame like this, and of course the eyes will be at the corners. Do you think that this will be a stable configuration? Certainly not. Why? Because if any load is applied, like this one, so what will happen? It will collapse. So if we want to make it stable, what we have to do, we have to add a member, we have to add a member diagonally from this point to this point. Now you can see that this configuration will be very strong. It will be stable. Why? Because a triangular configuration is very strong by geometry. It will not collapse. Like, for example, if I take this example, here is a triangle. If I apply some load on its apex, what will happen? The result will be that this node will go down, and these nodes, they will elongate to these points, and the form shape will be something like this. Right? Even though there will be some deformation, but this will be in a stable position. Now we have noticed that this bottom chord is in tension because it is elongated, so we can say that here it will be in tension, and these members, they will be in compression. That means in such a configuration the bottom chords are always in tension and the upper chords are in compression in general. Now let us assign some numbers to understand. Say for example, this is node number 1, this is node number 2, this is node number 3, and this is node number 4. And how many members do we have? Member number 1, member number 2, member number 3, member number 4, and member number 5. Now if this frame is supported, we know that this will be supported on a hinge at one location and on a roller support on another location. So at hinge we expect two directional forces or reactions, but in roller support there will be only one. So if we count say n is the number of members. So here we can see there are 5 members. So in this particular example there are 5 members. If we want to count number of joints, so we can see that there are 4 joints. So let J be the number of joints. So here it is 4. And if we see the reactions, so there are 3 reactions. Let R be the reactions. So there are 1, 2, and 3 reactions. Now we want to solve this problem. If we want to solve this problem, that means we should know what are the unknowns and what are the knowns. The unknowns are the number of forces in the member and the reactions. So every member will have only one force. Either it will have compression or it will have tension. And the number of reactions are R. So that means we can say that number of unknowns are n plus R. And how many knowns do we have? Every member can have two equations, that is sigma fx equals to 0 and sigma fy equals to 0. So we can say that number of knowns, this should be equals to two times at the joints. Now if this is a determinate structure, that means we can easily calculate the number of unknowns, then very simple is n plus r should be equals to 2 times j. So this is the governing equation. If it is satisfied, this is a stable structure, or this is called a determinate structure. Now the question arises, if this equation is not satisfied, say what if n plus r is more than 2j? Let's see this situation when n plus r will be more than 2j. Let us take one example. Say we have some frame like this, and of course they are joined internally. So that they will form a stable configuration. And of course these are all pinned connections. So in this particular case, how many nodes we are talking about? 1, 2, 3, 4, 5, 6, 7 and 8. And how many members we are talking about? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Now suppose the support condition is such, like here it is a pin connection and here also it's a pin connection. We know that from equilibrium equations we have sigma fx equals to 0, sigma fy equals to 0, and then sigma m equals to 0. So that means we have 3 equilibrium equations and we can evaluate only 3 unknowns. But how many unknowns are here? We can see that one will be the vertical reaction over here, horizontal reaction, vertical reaction, and of course some horizontal reaction. So that means there are 4 reactions. So we can say that here value of R will be 4, value of number of members will be 13, so n will be 13, so n plus n plus r will be equals to 17. The number of joints here are 8, so 2 times j will be equals to 16. That means n plus r is now greater than 2 times j. So in this condition, we cannot solve this problem easily. We have to use some different techniques. So what we say that this is called indeterminate structure. We have different techniques to solve indeterminate structure, which I am not going to discuss now. Second thing, suppose I remove support from one side. Let me remove the support from this side. So no more reactions, no support. So this joint number was 5. Now what is the situation? Now the situation is now R is equal to 2 only. So n plus R is equals to 13 plus 2, which is equals to 15. This is less than 2 times j, which is 16. Now we know that this structure with only one hinge support will not be stable, it will collapse. That means under this condition it will be unstable, or it will not be in equilibrium. Let me correct it, or I can say that stable or not in equilibrium. That is not in static equilibrium. There are special cases where it will not be in static equilibrium, but still it will be in equilibrium. So we are not discussing that issue. We are only discussing static equilibrium cases. Now let us take some examples. Like for example, this is a very classical example. Let us copy and paste over there. Let us paste it over here. Let me resize it. Let me place it in this corner. Now you can see that in this truss already nodes are numbered and the forces applied are two vertical forces. One is at, sorry, let me clear these unnecessary dots. So here we can see that there are two forces acting downward, 20 kip over here at node number 3, 20 kip over here, it is acting at node number 4. Node number 1 is a hinge support, so there will be two reactions. Node number 2 will have only one reaction. So let us assign reactions over here. No, it should be other way around. Suppose one reaction is here and the another one is here, and of course the third one is here. Oh. Let this be X, this be Y, and this be R. If you want to know unknown, so what we have to do, we have to apply simple equations. Sigma F X equals to 0. That means all the forces which are acting along x-axis, their sum should be 0. The force which is acting along positive x-axis is here, x. The another one which is acting also is here, that is H3. So that means x plus H3 will be equals to 0, or x plus 10 kip will be equals to 0. That means this x will be minus 10 kips. What this minus sign indicates? That the direction which we assumed or we applied is not correct. The actual direction will be something like this. The actual direction will be like this, right? Now we can apply the second equation, sigma Fy equals to 0. In y direction we can see that there are two forces acting upward. That means y plus r. This will be equals to 2 downward forces, which is 20 here and 20 here. That means 20 plus 20, which is equal to 40 kip. So the equation becomes y plus r is equals to 40. Now we can apply this condition, sigma m about node number 1 is equals to 0. So that will reveal that first this r, it will give a anti-clockwise rotation, So R is multiplied by 8 plus 8 is 16 feet, and this will be equals to this 20 acting at node number 3 will be passing at 4 feet. So that means 20 multiplied by 4 plus this 20 is acting at mid of this member, so that means it will be 8 plus 4 is 12. That means 20 into 12. So this will give us 40 plus 240. That means this will be equals to 320. So R will be equals to 320 divided by 16. That means R comes out to be 20 kilonewton. So from this equation, if R is 20, definitely Y will also be 20 kilonewton. So these are the support reactions which we have calculated now. So this is the way we calculate the support reactions for determinate structures when there are 3 unknowns and we have only 3 equations to get these unknowns known. Now comes another term which is called a free body diagram. So what is a free body diagram? So for a free body diagram, let us remove all these and apply the actual forces. First of all, this x, which is minus 10 kip. This equals to 10 kip. We need not to write negative because already the arrow indicates the negative direction. Then at both these locations, at both these locations these forces are negative 20 kip. Sorry, 20 kip, not negative, and the arrow indicates the correct direction. So this is the free body diagram. Now we want to know the internal forces in this member. So what we can do, we can take, say for example, this node and see what's happening over here. So we can draw one member like this, another member like this. There are 2 members. This is member number 5, 2. This is member number 4, 2. And there is a force acting in upward direction which is 20 kg. Now, if this system is in equilibrium, that means each and every node is in equilibrium. So this is x-axis, this is y-axis. So what we have to do, we can again apply the same equations which we have already applied before and try to solve it. Here, if we apply sigma f x equals to 0, since all the sides were equal, so this will be equal to 60 degree. Say the force in this is acting in this direction, the force here is acting in this direction. So if we say sigma fx equals to 0, what does it mean? That means force in 52, this is negative, negative force in 42 with cos component should be equals to 0. And when we say sigma fy equals to 0, that means force in 42 sine 60, this is upward direction, plus, and 20 is also acting in upward direction, plus 20 will be equal to 0. So this is our, say, equation number 1, equation number 2. If I solve this equation number 2, I can say that f for 2 will be equals to negative sign into 20 divided by sine 30. Sine 30 is half, so it will be minus 40. So that means f42 will be equals to minus 40 kips. Minus means what? Minus means negative direction. So this direction was not correct. Now, if we take our equation number 1, so we can say from equation number 1 minus f52 minus f42 is minus 40 into cos 60 equals to 0. That means minus f52 minus minus plus 40, and cos 60 is 0.866. This will be equals to 0. So I can say f52 will be 40 times 0.866, something around 34 kips or so. So that result gives a positive force of, say, 32 force or 32 kip or so, whatever. That means our f52 is in correct sense, but f52 is in reverse order. So let me draw this figure once more. Let me draw this figure here to make it clear. "20" is acting upward, fine. F52 is acting in this direction, positive sign, correct. And one more, let me select one more color. How many colors I have? Let me select this one. And F42 is, sorry, F42 is acting in this direction. Now, this is 20 kip. This is F52 is something around 40 multiplied by 0.866 is how much? Let me calculate. Just 1 minute. Multiplied by 0.866, 34.64. So this is 34.64 and this is 40. Now we notice that the direction of internal forces in the members. This is our member number 52. This is member number 42. Now, let us take this example of member number 52. This member number 52, it has a node over here, another node over here. And the reactive force is something like this. That means the applied force is something like this. This applied force is coming as a component of this one. And on the other side of the member, of course, the reaction force will be here and the applied force will be in this direction. That means if a member is in tension, so both the forces, they will be acting inward. I mean, the arrows will be indicating inward. This is sign convention we use for tension members. So this is a tension member. And it's converse, that means if a member is like this and the external forces are acting on this, like this, and from this side, sorry. So if the external forces are acting like this, there will be internal reaction developed, and it will be like this. So if a member is like this, or in compression, the arrows will be away from each other. This is the sign for compression members. That means the tension or compression, it is the indication of the internal forces, not the applied forces. So far we have completed our today's lecture. Tomorrow or after this, we will develop another one where we will calculate the internal forces based on either method of joints or method of segments. Thanks a lot. Goodbye.